All right, we're going to start the next session on performance optimization. Two parts. One is about scripting performance, and the other is about graphics performance. We're starting with graphics performance. So when you're trying to figure out why my game is running slow and how do I make it fast, you first have to figure out why is it actually slow. And there are multiple reasons for that. The first one is fill rate. Fill rate basically means the screen pixels, so your resolution of the screen, multiplied by overdraw. Overdraw is basically how many objects are you drawing on top of each other. So if you're walking through the terrain, for example, and there are hundreds of swaths of grass on top of each other, then you have an overdraw of 100, and that's really expensive. The same if you render a room and you don't do any occlusion culling and you render several rooms after each other in a house, then you get overdraw. The second thing is shader computations. Usually that's not really a big problem because before you run into shader computation limits on graphics cards, you usually run into fill rate issues before that. So don't worry about it. Vertex count these days on actual graphics cards, it's not an issue anymore really because high-end graphics cards, depending on your shader, they can really push like 30, 50 million polygons. And of course there's one important exception, and for a lot of people that exception is quite important, and that's integrated graphics cards. Because there you have like a budget of maybe 30,000 triangles per frame, and it's very little. But that's what level of detail is for, turning off pixel lights and turning them into vertex lights and things like that. And lastly, and one thing I'm going to focus on, is draw calls. So draw calls, there's one reason why draw calls are really bad for you. Draw calls, they basically tax the CPU equally much to the GPU. So that's pretty bad because you're running your game on the CPU. You need to run your physics, you need to run your game code, you need to do some raycast and all those things. And you want to have that reserved for the CPU. And if you use the GPU properly by just rendering loads of triangles and vertices and expensive shaders, they can work in parallel. But if you're bound by the CPU, then it's just the CPU is going to be the bottleneck and it's going to be used by those two processors. And that really slows down performance. So on a modern machine, you have around 500 draw calls per frame. So the question is, what is a draw call actually? Because it is not the number of objects in your scene that are being rendered. Because if you, for example, have a pixel light in your scene, then that object has to be rendered twice. If you have 3 pixel lights affecting one object, then you have to render it 3 times. Now, of course, you can have a lot of lights in your scene, and different lights affect different meshes. So you usually end up having like 2 pixel lights per object. But still, it's just important to know if you have 2 pixel lights per object, you're rendering the object 3 times. Same thing with if you have multiple materials per mesh, each material adds one more draw call. So draw calls, they easily add up. And of course, there's one solution to that, and that is combining. It's extremely important because if you have lots of objects in your scene, that's bad, your game runs slow, and, well, we don't like that. Now, there's one right way to combine objects, and sometimes people make mistakes when they combine objects, because you should only combine objects which are close to each other, not objects which are far apart. So if you combine too much, that can actually hurt performance more than not combining at all. which seems a bit counterintuitive, but we're going to show why. So no combining, pretty bad, lots of objects, CPU gets taxed, high draw count, your game runs slow. Good combining. We combine objects which are really close to each other, and we try to use the same material. So for example, if you're doing an indoor scene, you're rendering a house, what you're really shooting for is that you have one draw call for each room. So you have 20 rooms in the house, so you have 20 draw calls. Now, if you look around, you have the ceiling, you have the walls, you have some lights up there, you have the windows, and you have the exit sign, you have some textures on top. And the question is, how do I put that all into one draw call? And the answer to that is, of course, using texture sheets. So basically, you combine the floor texture with the ceiling texture, with the window texture, with the exit sign. You put it all into one texture, and then use smart UV mapping to use the same texture. And that way, they're all using the same material, and you can combine them. So the rule of thumb: combine objects that are like around your object size or your point light size. So when does combining go bad? You should never combine objects which are really far apart. The reason for that is if you have one object, let's say we had those objects as separate tables. So we want to render those tables here. Now, if we combined everything and I was looking in that direction, then I would still be drawing those objects behind me because they couldn't be culled because they are drawn as one object. So the bounding volume of this object would be pretty big. It would be basically the entire room. So I would still have to draw the object behind me, and that increases the vertex count, of course. So that's possibly not what you want to do. And also, for combining, it doesn't make sense to combine objects when you have more than, let's say, 3,000, 4,000 polygons. Because at that point, it doesn't really cost that much more to make one more draw call. So the other reason why it's really bad, and I swapped the slides here if you got a bit confused right now. So the other problem is if you have a large object and you have multiple lights sitting on top of it, then those lights have to be thrown, then you have 3 lights per object. If you didn't have it combined, let's say there's a light over here, a light over there, and a light over there. Now, if you don't have them combined, there's 1 light per object. If you have them combined, there are 3 lights affecting 1 object. And that's bad for the pixel shader performance. Because basically you have to render the objects in one pass for the first light, and again for the next, and again for the next. And you have to do it for the entire mesh. So I'm going to give a demo to demonstrate why it's bad and how to fight it. Okay, so I made a small test scene which really demonstrates the worst case. So what I have here is I have 2,500 little cubes with each that's 12 triangles each. And there are 20, no, there are 1, 4, 8, so that's 40 lights. And in this first test, nothing is combined. And of course, it takes a long time. And now we're getting 5 FPS. Great. So now in Unity 2.0 we added a stats button in the game view. And that shows you where your performance is going. So you can see here, you have a triangle count of 100,000 triangles. That's pretty good. That's average scene. That's sort of what you should be shooting for. Now, to the right, you see the draw calls. We set 500 to 1,000 max, and we are at 10,000. So that's pretty bad, and that's why this is at 5 and not at 100. So the next step, if we want to optimize this, is to combine all the objects into one. So basically, in Unity, you can you have a script called combine children. You can just attach that to a game object, and then all the children automatically get merged. And Unity can, of course, only do that if they share the material. If they don't share the material, you can't combine them. So that's why you need to plan ahead when you're modeling your rooms. So that's why you use the texture sheets. So I'll hit play again on this. And performance is already a lot better. We're getting 33 frames per second, roughly five times as fast. So the draw call count is up to 43 now. That's because we have 40 point lights. I mean, of course, this is a kind of a crazy scene to have, like with those pixel lights being drawn. But you can see the triangle count and the vertex count. It's all of a sudden 2.5 million. So before, when we didn't combine, we had 100,000 triangles. So what happened is that we combined all the objects, and now all the points affect the entire object, so it has to be drawn 40 times over. So that means this object, which is 100,000 triangles, has to be drawn 40 times, so you get 4 million triangles. And that's just a huge waste. So what you're really shooting for is to combine objects which are close to each other. So here you can see we're getting 100 frames per second, and I'm pretty sure it would go a lot higher if we didn't cap the frame rate at 100 frames per second in the editor. But you can see the draw calls, it's 200, it's a good size. Triangle count, it's doubled compared to the uncombined, but that's okay. It's not so bad. It's like twice as much because there's some lights who are affecting the other part. Because I mean, basically, we combined them so that, like here, that's one object, that's one object, that's one object, that's one object. And of course, this light, it leaks a little bit into this one, so you get a bit of overhead. Yeah, so that's basically what you get from combining. So we started with 2 frames per second, we ended up with 100, and we were limited by the editor capping the frame rate. So that's why you should do combining. Of course, the performance you actually gain in practice, it's not going to be that much because this was just a real worst case scenario. But in games we have easily seen like a 10 times performance improvement. So the goal is just try to get like 4,000 polygons into one batch, and then you're golden. And of course, make sure the size of the geometry matches your point light size, so that you really optimally only affect the part which should be affected by the light. So the next thing, what are lights actually for? Dynamic lights. Now, question is, why not static lights? Well, the talk is about performance. So why not use a lot of static lights to light up your scene? Because it looks really good. Because actually in practice it doesn't really look really good, because light mapping would look a hell of a lot better. Because if you do light mapping, you can combine an infinite amount of lights. And you can you can do all kinds of fancy stuff. You can do global illumination. You can bake your ambient occlusion into it, and it will run a hell of a lot faster than having only like 2 lights in your scene. So the trick now is, I mean, we didn't do the dynamic lighting in Unity all in vain, because you can combine the two. So what you do is, you have a base light map, your static lighting in this room. So you decide, those lights, they're never going to change, they're not really moving, and I can't shoot them out with a gun or whatever you have. But then maybe you have a guy running through the scene, and either he has a rocket launcher or a torch, and then it affects the geometry on top of that. So you just get a really nice effect of the torch walking through. You get really big, good performance because you have all those lights which are combined into a static light map. It looks nice. You get global illumination on it, and then on top you have a dynamic light, so it looks great when something moves. So there's of course one problem. You actually have objects which are moving in your scene, and of course they can't be light mapped. So what to do? So you use culling masks for that. Basically, you make a rig with your lights in Unity as well, where you set up the culling masks to not affect static objects. And that means you have all your characters in one layer, let's say the enemy layer. Then you set up your light culling mask to only affect that layer. And then it will not light up any of the static geometries, so you still get the fast performance, and the moving objects, they just get affected by whatever lights are close by to them. And that's really the best of both worlds. So how do you actually create a light map? Now in Unity, there's no built-in light mapping functionality, at least at the moment. So light mapping is done in Maya or other rendering tools like 3D Studio Max, Cheetah 3D, Blender. It's really easy to import though. Basically, you just import your Maya file, you select the material which your object is using, you switch to one of the light mapped shaders, and you're good. So for those of you who have never done light mapping before, Ethan is here. Ethan, maybe stand up. He's our Maya expert, and if you want to, you can talk to him, and you can have a one-on-one session with him, and he'll show you everything you need to know about Maya and light mapping. And also Thomas is here. Thomas, he knows everything about 3D Studio Max. If you're using that, how to set up the light mapping, he'll show you.
And V-Ray.
And V-Ray. Woo. Okay, so now I'm going to give a small demo of what light mapping gives you and what point lights give you and what you should really use your point lights for. So this is one of the launch demos. It's called Avid Fate. Okay. It's basically we had a graphic artist intern, Raimund Schumacher, who made all the artwork for it, and then we had Forrest write scripts and particle effects and make it kick ass. So it's basically like some first-person shooter walking around shooting up robots and big-ass robots and rocket launchers, and you know, probably seen it before. So we have all those nice lighting effects here. Like for example, here you see like the floor. It has lights casting. They are all pre-computed, static lights. Looks really nice. You have global illumination. They are soft and everything. No need to use shadows and waste performance on that, because we have plenty to waste performance on otherwise. So what we do instead is we have a point light on every bullet here. So that just really adds a lot. What doesn't add a lot is if you use a lot of point lights, because you're basically just wasting performance there. And it's just much nicer if you use it for something good, like a rocket launcher. Where's the door? There. So you can see that just, yeah, that's the way. And of course, you can use your bump spec lighting on the. Oh my God, they're coming. No, that was easy. So yeah, use your lights wisely. Don't waste them. Spend too much time to let them to waste. This brings us to the second part of the presentation, which is optimizing script code. And the first thing when optimizing script code is you have to be aware what functions are slow and which ones are fast, and which ones should I not be calling every frame, and especially which ones should I not be calling every frame several times with the same arguments, because you could just store them and reuse them. So there are a couple of utility functions in Unity which may be pretty slow, and they're really useful, but if you care about performance, then you want to optimize them away in certain cases where your game is slowing down. So the first thing is raycasting. That confuses a couple of people, but I mean the thing is, if you have a big mesh with like 5,000 triangles and you want to cast a ray against it, and there's probably not only one mesh in your scene with 5,000 triangles, then no matter how efficient our quad tree hierarchical searching for the raycasting is, it's still going to take up performance. And just try not to raycast against meshes. That's the easiest way to optimize it away. So, for example, one way would be you could use culling masks. So very often, for example, you know, I only want to find out, I want to only raycast against enemies. So why cast against against the room? There's no reason to do that. So you just use a culling mask on the raycast and just say, I only want to cast against the people here and not against the room. And then you don't have any mesh colliders to cast against, and everything runs fast. Or another thing, sometimes it's not really necessary to do a raycast every frame. Like, for example, if you have an AI and you want to know, am I going to be running into something? Should I try to avoid it, steer away from it? So just do it every third frame, do it every 0.5 seconds or something. It's often enough, doesn't look bad. You could even do fancy things like increase how often you do it based on the distance to the player, because those objects that are miles away, I mean, no one's going to see them anyway. So if they do something stupid, who cares? So one thing that a lot of people do is like find game objects with tag, game object.find, find objects of type. They are not the fastest functions to use. You shouldn't use them all the time. You should optimally avoid calling them in the update loop, and you should most definitely avoid calling them inside inner loops where you go through something several times. So those calls, they can really add up very quickly, and there's a solution for it. So let's say you want to have a player. You have a player in your scene, and you have a lot of enemies trying to track down the enemy and try to shoot at him. So you might use GameObject.find and then the name of the player. That would be crazy slow. The second you could do is you could use find GameObject with tag. That would be faster, but it's not the fastest way to do it. The fastest way to do it is to just have a static variable in a script and say var the player colon the player control script. And then when the player spawns, he just inserts itself. He just says, "Okay, I'm here," this and sets up the static variable, and then all the enemies can just access it, and it doesn't cost any performance because Unity doesn't have to go through some objects and find the object by name or by tag and do all this dance. So it's just a lot faster. So another case is where you have a lot of objects of the same type, and you want to get to all the components of the same type. So you could use find game objects with tag for that, but instead, why not just use a static array list and then on enable and on disable function calls, which get called when an object gets instantiated and is active, and on disable when it gets destroyed. Why not just add yourself to a static array list, put them in there, and then you have the array list always ready. You can walk through them, and it's incredibly fast. So the next thing, I mean, sometimes when we look at games people do and they run fast, it's just because all the scripts on the entire level, they are running all the time. And you might think that's good, but it's not, because if you run the scripts I mean you basically have a limited CPU budget and you have to live with it. So I mean, if you have like 500 enemies in your level, you're just not gonna run AI on it every frame all the time. So what you do is you probably can't see the enemies which are far away anyway. So why update them at all? So you basically just have them far away. You completely disable them, and they just don't do anything. And then when the player gets close by, you start updating them. And sometimes people think, yeah, well, I'll just put a function update, if far away, then return. And no, that's not the way to do it. Because basically, then Unity has to go through all those objects and call this function, and then you have to check if it's far away, and then we return. And if you have 500 objects, that really adds up. So don't do that. Instead, you can just write enabled.false, and the update loop will be disabled. Problem solved. So the question is, how do I figure out if a player is far away or not? So there are basically two ways to do that. Either you have like a loop running in a coroutine. So you basically check in a coroutine every 5 seconds. Is the player now close by? No. Yield, wait for 5 seconds. Next. Yield, wait for 5 seconds and check again. And if it's close by, you enable it. The other way to do it is to use triggers. So basically you have an on-trigger enter and an on-trigger exit. And you just check if the player is in the trigger zone. If he is, you enable it. If he goes out, you disable it. And you can just do that for a lot of different things. Like, for example, pickups, rotating pickups. They are like miles away, and they are being rotated. Why? They're so small, they're not even visible. So that's those two optimizations. That's really usually the biggest ones you can do. And now we're sort of moving a bit into low-level optimizations. So in Unity, you get performance which is pretty close to what you would have in C++. It's around 50% of the speed. And that means you actually can think about it in the same way that the C++ programmers think about it, and that is in cycles. So, for example, if you add, subtract, or multiply a floating point value, that's usually a couple of cycles, 1 to 3 cycles. Now, division, that's often very surprising, but it actually takes 30 to 40 cycles for a division. And it's also important to remember there are a lot of divisions implicitly. Like, for example, if you do a normalize, that's actually pretty expensive because it has to do a division, has to do a square root, and so on. So Then there's square roots. Square roots, sinus, cosinus, they take up 60 to 100 cycles. So very often, I mean, you can see you can do 100 multiplications in the same time you can do one square root. So very often you can just optimize your code in such a way that you just get rid of the square root or the sinus function, or like you're rotating some object around something. I mean, you could just use the animation system for that, or yeah. So square root and normalize. Normalize functions are very common in games, of course. Like when you try to get a direction, I want to know I'm here, you're there, what's my direction, and you want to normalize that because you want to walk along a constant speed along that direction. So what you have to know is that a normalize basically looks like this. It takes the vector and it divides by the square root of the vector x component multiplied by the vector x component plus vector y component multiplied by y component and vector z component multiplied by y component. Now, that part isn't so bad. This part is bad and this part is bad, because that's the one that's the 60 cycles for the division and 40 cycles for the division and 60 cycles for the square root. So normalize. Don't just spread it around just for fun. Use it where you have to, and otherwise avoid it. So for example, one thing where you can avoid it is if you do a distance check, for example, you just, you know the distance based on like, so let's say you write the script which checks how far away am I, and then I disable the object. So you would write distance larger than magnitude, and then return. So what's wrong with that? Implicitly, if you calculate the magnitude, that does this in here. So that gives you 100 cycles. And that's not very fast. And you can make it around 10 times faster. So the way to do that is to use the square magnitude. So with some simple math, you can just figure out. So you take the square magnitude, which is the magnitude multiplied by the magnitude. And basically what this does is you take this whole thing and multiply it by each other, and then you can basically take out the square root and you just have this part. So when you have that, you have the square magnitude, and now you need to multiply the other side so you get a square as well. So you multiply the distance by the distance, which is really fast, one cycle. And this one is also really fast because it just has some multiplications and some additions. Something like that, that can run in 10 cycles. The other one is running in 100. So you can save a lot there. And finally, one thing you have to think about is the cache. So basically, a computer works like this. I mean, you have registers. There are very few registers, 32 of them. Then you have different caches which kick in. So for example, you have a level 1 cache, which is really fast. You can load from a level 1 cache in like 10 cycles. Then there's a level 2 cache, which is slower. And then there's RAM, which is really slow, which is like 100, 200 cycles to load from. So since you only have 32 registers, you really want to make sure that you do all your operations on the same variables at the same time, and you don't spread them out all around your code. And another thing that you have to remember is when you call into Unity functions, that can very easily wreak havoc with your cache, of course, and that can lead to performance degradation. So, for example, everybody knows transform.position, and everybody uses it a lot. But I mean, what is actually going on behind the scenes? Because it seems so harmless, but it's not. Because if you write transform.position, the first thing that Unity does, it gets to the game object. No, actually, the first thing it really does, it has to call a function from C# into C++. So that's one function call, 10 cycles or something. Now, then it has to find the game object. That's really fast. That's just a pointer lookup. Then it has to find the component, the transform component. Now that can be a bit slow because it has to go through a couple of components and find it by type. Now, let's say that's like 50, 60 cycles. And then that gets returned to C# again. And then we enter C++ code again. And we ask for the position. That calls a function in Unity again with that specific transform. And now we will go through the transform. And of course, it may be that your transform has a parent, so you have to walk up the hierarchy to figure out where it actually is. You have to apply scale to all the objects, rotate children, and so on. So it's, I mean, transform.position can add up, and it does. So if you use transform.positions in inner loops, it can really easily become a bottleneck. And by just caching the position somewhere, you can just make things run 100 times faster, which is quite amazing. And then lastly, about the cache, is how do you walk the memory? So the thing is this, if you have a level 1 cache, for example, and you want to go through 100 objects, now you could have them all spread out, and that's really going to trash your cache, and you will have to wait 100 cycles every time you try to access something. So you really don't want that. You want to keep your objects together, tight. So, for example, in the case of a Boyd script, so everybody knows what a Boyd script is? Question? No? No? Okay. So Boyd's is basically like, it's some very simple algorithms which you can use for birds that flock around, and it's just some simple rules that that basically say so all the Boyds they try to move in alignment, for example, because that's what birds do. And then when they're too close to each other, they try to push aside, so they change their velocity to always have a certain distance, but try to align themselves moving forward. And there are many different ways to go about it, but if you use a struct with vector 3s, then, for example, if you have an array of vector 3s, then you can actually walk through that memory without trashing the cache, because everything will automatically be preloaded by the cache, and it's just a lot faster than finding each object, getting the transform position, caching it, then getting it from Unity, going through some functions to get it, and so on. It's like you can actually make things run 1,000 times faster by taking care of those things. And I mean, on the other hand, of course, there's, I mean, if things already run fast, then I mean, machines today are really fast. So I mean, sometimes you just don't care about making it 1,000 times faster because it's not actually going to make your game run 1,000 times faster. So then there's, of course, JavaScript. So the first thing is dynamic typing is slow. It's really dog slow. So you should really try to avoid it. If you use static typing, you can get the same performance as you get in C#. And basically, that's around 50% the performance you would get from optimized C++ code, and is around 20 times faster than Mozilla JavaScript. So how do you make sure that, that in JavaScript you don't end up using dynamic typing? And there's something called pragma strict. And basically what pragma strict does is it completely disables the ability to do dynamic typing per script. So you can just decide, okay, this script is really bad, it's really slow, and I need to optimize it. So you just put in a pragma strict, and then you'll get a bunch of compile errors for all the parts where you're using dynamic typing, and then you fix those, and magically everything will run faster. So to illustrate that, I made a small demo where I made a couple of Boyd scripts, and it's basically the 6 different ways of how not to do Boyds. So I have this this script here, which is basically we're running 400 Boyds at the same time. We have a script which just instantiates a prefab, like we have this little birdie here. This guy, whoops, what's going on? No likey. Okay, so we have this bird here, and he's just going to fly around. So at startup, we instantiate this guy 400 times, and then we have, I've implemented 6 different ways you can do Boyds. And we're going to start with the slowest one. So I'm going to show the script here. Vehicle tags. Oops. There we go. Okay, so it's a pretty simple Boyd script. Basically, we just have this update routine, and we basically just have like a steering force. We add to the steering force like a little bit of randomness, and then we update the velocity with the force. So we just add the force multiplied by delta time, and then we update the position by just moving the object using the velocity and multiplying by delta time. And then we just make it always look in the direction of its velocity so it doesn't like fly backwards. So the things that are slow in this script is the apply alignment function and the apply separation function. So I marked the things that are slow here, or that are extremely slow here in this case, and which we're going to optimize in the next script. So here we're using find game objects with tag inside the apply alignment functions. Now, we're doing this 500 frames per second because we have 500 Boyds. So this function gets called 500 times to find all the neighbors. Then we go through all the neighbors, get the vehicle object, and add its velocity. Basically, the purpose of this is finding the average velocity of all the birds and then making them sort of lean towards that so that they attempt to fly in the same direction, but they, of course, also have some randomness, so they'll go a bit around but try to steer in the same direction. So we'll just give that a shot. All right, so performance. Where the hell is the FPS counter? Ah, there it is. It's so slow. Yeah, it's what is it? 0.8 frames per second. Awesome. Well, I mean, it's a lot of birds, of course, but I'd say we can do better. So the next step, well, the first step is we use a built-in array of objects. We no longer use the find game objects of tag. Like here, we have a static variable up here called all vehicles, and it's just a built-in array with all the. It's a static variable with all the vehicle with all the vehicle scripts, and we basically set that up in our instantiate function where we instantiate those 500 things, and then we just fill out this this array. You can do that in many different ways. You can do it dynamic if you want to add more or something like that. So what we did here is we removed the game objects find with tag. And now the only thing we have to do is we have to go through all the vehicles and add positions and do some kind of funky math to make them separate when they're close together. And here we apply the average velocity. Just add the velocity, average it, and then align towards that velocity. So just removing game objects find with tag. Let's see. That's better. So we're getting 4 FPS. Well, I mean, it was 0.3 before, so that's already 10 times better. It's quite something. So, next step. Built-in array, cached position. Now, what we did before, I mean, what we had talked about before, I mean, I explained what transform.position does. And it sounded pretty scary. But, of course, I mean, in reality, if you just have like 500 objects in your scene and you just write transform position one time in each, that's no problem because computers these days, they're crazy fast. So don't worry about it if you're not writing inner loops. But the real problem here is that we go through 500 voids in this script, and then we go through all the neighbors, which is also 500. So this loop here, this line here, that gets executed 500 by 500 times. That means 25,000 times. And that's something that computer science calls order n squared. And it's pretty bad for you. So the main problem here is that, no, I was looking at the wrong thing. So the slow part before was in the apply separation function. Basically, the apply separation function takes the difference between this object and the other object. So it goes through all the other objects, takes the difference, and then it does some fall-off curve so that when it's far away, it's not going to add to this separation velocity, which will add to the object. So instead, so basically, before we were writing transform.position and all vehicles dot get component vehicle dot transform dot position, subtracting that, and that was really slow because when you do it in inner loops, and in this case 25,000 times per frame, getting the transform, getting the position, that gets slow. So instead, what we do is we calculate the positions in an array. We update this array one time. We have this array here, all the cached positions of the voids, and we get the transform position once per frame. So we only do it 500 times and not 25,000 times. And then in the script down here, we can very quickly access it, and we don't need to write the transform.position anymore. Instead, we just use the index of the void to look up the position, and it's all nicely done in this array. It's all nice in the cache, and I think it's going to run a lot faster. So okay, so we're getting smooth here already. So it's 17 frames per second. So that was the only change was transform.positions, instead of calling it 25,000 times, calling it 500 times, and instead just caching the positions. So 5 times performance improvement. Next, optimizing it some more. Let's see. So before we talked about normalize. What was slow here, I'll just bring up the old script. Basically, the math we did here, we had this position difference dot normalized multiply by, then we have a division, again expensive, and then dividing by a square magnitude. Now, I mean, it's just a fall-off curve. So if it's a bit different, oh well. So we'll just change it around and make it a lot faster. And I mean, who knows how birds, I mean, what the fall-off curve for birds is anyway. So yeah. So we take instead the position difference and we divide by the square magnitude. So there's no normalize anymore. There's no square root and so on. So we try that. Cached optimize. All right, before we had 17 FPS, now we're at 21. Now, oh well, 25, wow. Okay, so it added quite a bit in the inner loop, but of course it's not the most we can get out of it yet. So we optimize it a bit more. And of course, one thing you want to do, you want to be smart. So one thing we did here, for example, in the apply alignment, was we go through all the vehicles, we add the average velocity to each other, and then we divide by the velocity, so we get the average. Now, those things, they practically stay the same. I mean, they don't change so much when you update one void. So why not just move that out and do it only one time per frame instead of 500 times per frame? So that's what we do here. We basically have this update cache positions, which is getting called once. So we go through all the scripts in the very same way, and we add up the average velocity. Then we store the average velocity in a static variable. And in the apply alignment, we can completely get rid of the loop. So we just only have to say average velocity minus velocity, and then we do some funky stuff to make it sort of look right, but which isn't all that expensive because you don't have this inner loop of doing things 25,000 times anymore. So we take a look at that. And better, 25? You must be kidding me. Nah.
You didn't change the script to the next.
Did I? All right. No, I did. I mean, I presume that it looks a little bit different. I mean, of course, what taxes the CPU here as well is, of course, when they go out of bounds and so on. So I probably set up some of the values a bit different, so they behave a bit different. But it should be around 20% faster or something like that. Now, the last optimization we can do. Now, the actual problem in this is really the amount of neighbors we have is just crazy. And the function that was really slow was always this apply separation. The problem here is that, I mean, basically all we wanted to do is we want to separate those that are close to each other. And in the real world, you don't have a lot of birds really close to each other. And you can just say, if they're further apart than 5 meters, we don't care about it. So you can say, if we could just get those 500 iterations down to like 10, which is going to be close by, then we're going to get a lot better performance. Now, of course, the tricky part is how do you actually figure out your neighbors? And what works great for that is triggers. So what we do is we add a rigid body to the bird, we make it kinematic, and then we add a collider to it, and we make it a trigger. And that means we get the onTrigger enter function and the onTrigger exit function. We check we get the vehicle class, and then we just add it to an array, which is like an array per object. So each object basically tracks all the objects which are nearby, and the trigger tells us when it is. And you can tweak the trigger size to make it smaller so that less objects will affect it. So we have those onTrigger exit, we add to it, we move to it, and then we simply walk through the neighbors. So instead of 500 objects, we walk through, let's say, 10. And now we're at 33 frames per second. No, 44 frames per second. And it's going to get better as soon as they get further apart because, yeah, you can see it improves more and more. Because then, of course, less are in contact with each other. So that's another doubling of performance or something like that. And yeah, that I mean, the main thing is that optimizing optimizing the code like we did in the beginning, with like those rather low-level optimizations, like taking out the taking out the normalize and so on, that only gives you so much. What really gives you performance is being smart and figuring out what is actually slow, and that is having this inner loop which gets called 25,000 times, which is crazy. So just getting that down to 10, this line will only get executed 2,500 times. So that's the demo. I hope that explained a lot of the things we talked about before. And now there's questions.
Do you have any ways to profile your script?
Not right now. Well, I mean, actually we do. There's a script on the wiki. I don't know if it's on the wiki yet, but you can do it manually, where you basically add some functions calls at the beginning and at the end, and then it will print it to the console. And it works pretty well. It's not like the perfect Unity solution, and we know about this. We want to do this.
Back to graphics.
Yeah.
You said put the entire room in the same texture sheet.
Yeah.
What about texture size?
What about it?
I mean, if I would do it, I would take one, as you said, one texture for the exit, and make that only 64 times 64, and the walls would be white, 256 times 256.
Yeah.
And all those would probably be less than if I should put them together in a big texture sheet that would, for this room, would probably be 248.
But I mean, the thing is, they're not gonna. I mean, combined, it's not gonna get bigger, right?
Well, they should.
I mean, if I have a white texture, and then okay, I have the floor texture. You would say it's 64 by 64. Then we have the ceiling texture. It's also 64 by 64 and another one. So together, that's like 128 by 64. Well, if you combine it, it's also 128 by 64. So what matters is that at the end, you have the same amount of VRAM being burnt. And even if you don't combine, you actually should be combining your textures into like a good size is 512 by 512.
So 512 is a good size for Unity.
Yeah, I mean it's not a Unity thing. I mean it's basically what the graphics card like. I mean the main thing about the texture sheets is just that you can actually combine, because if you have it in separate textures, you can't combine, so you're screwed. Yeah, I mean of course, there's one downside to texture sheets, and that is tiling. But that can be solved. You can do some clever UV mapping, so that instead you mirror. So basically, you have you have this floor, right? So you have the floor like this. You have one tile like this. Then you set up your UV map that is like basically like this, and then the other side again.
Use polygons instead.
Yeah.
And flip the UV on each polygon.
So
you
get the
have
same.
the floor as one polygon, but you would divide it up each time.
You just use more polygons, exactly.
Yep. Okay, I get it.
Your question.
You call it dynamic typing in JavaScript is very slow.
Yeah.
What do you mean by that? It has to figure out how you're going to use a variable? It has to figure out it's a string?
Yeah. I mean, basically, dynamic typing means this. You have a variable, and when you're using the code, you don't really know the type of the variable. So at runtime, so let's say you call a function called do on it. Now, the runtime system then has to first find the function, and basically it almost has to look at it by string or something like that. So it has to go through some hash map, find the function, and then call the function. And that part is really slow. Now, I mean, it's like 10 to 100 times slower than a direct function call. So, I mean, as I said, I mean, computers are pretty damn fast. So if you do this like once per frame, or like in 20 objects or something, that's fine. but in an inner loop, this is going to totally wreak havoc with your performance.
So you simply avoid it by saying var blah point, I would say?
Exactly, you use the colons to define the type. And in Unity, in the JavaScript implementation, we have something called type inference, which is quite smart. Basically, if you write var p equals 5, then it can infer the type based on the assignment. So it would know, this is an integer, good. Then we just use the type, and then you're in the fast path again. So very often you end up in the fast path without knowing it. You simply you don't have to worry about it. But I mean, they're just like when you use get component, it doesn't know. So if you then call a function on it, it still doesn't know. And then maybe that function returns another value, and you think you're statically typed, but you're not. So that's why the pragma strict is really useful, because you just get a compile error.
Something you didn't touch on too much was skin mesh renderers.
Yeah.
You know, bones and stuff. Let's say you have a model like a car where you wanna make the suspension move and everything like that. Do you think it'd be better to separate out the non-moving parts that will never ever move into a separate mesh, and only have the actual skin mesh render with the bones and stuff? Like, imagine the suspension being one mesh, and then the sort of the hull being a separate mesh.
I mean, it's hard to tell, because I mean, of course, it just depends on a lot of factors, like the actual poly count you have. Okay. But I mean, for a car, the question is also, I mean, do you actually want to use a skin mesh for it?
For the suspension, so there's like sort of springs moving and.
So you have like a pretty complex bone system there.
I think there's only like 5 bones.
Okay, so you have for the car 20 objects.
The car, there's the wheels, the 4 wheels, separate objects, the actual hull, the car part, and then there's the suspension, the base of the car, which has the skin mesh on it.
I mean, I could imagine that the best way to do it would be to have the car and then the stuff, like the wheels, the suspension, and so on together. Okay. That could work, but I mean, it's just try it, because I mean that's the only way to really find out.
Depends on. Does each one of those vertices have to get transformed because it's in a skin mesh? So
I mean, basically, the disadvantage of skin meshes is always that it has to be updated every frame. You have to upload to the graphics card the transformed meshes. It taxes the CPU and so on. So, I mean, it's a trade-off. It can work out either way. Okay. Thanks. You're welcome. Yeah.
You just mentioned now that making the hash call to look up things is slow. Our hash is slow, I use Booz, so I use a lot of hash calls.
Like a hash table?
Yeah, hash tables.
No, I mean, hash tables are pretty fast, but compared to no overhead at all, it's pretty slow.
But yeah, okay. So they are reasonably fast.
Yeah. Using raycast as an alternative to mouse over, say like to get a game controller with a draggable cursor, is that significantly more overhead? Or are there any ways to optimize that?
To tell you the truth, the on mouse over actually does a raycast. So if you do another one, you waste one.
Well, we have to use it instead because the cursor doesn't move the mouse.
I mean, basically what you would do there is that you use the culling masks. So you don't, if you have a complex background geometry that you can't click on anyways, okay, put in a box collider instead if you want to block whatever's behind it, or just ignore the problem and just shoot straight through the building because that's how you get it fast.
Raycasting culling masks, that's key.
Yeah.
Is there any difference optimization between the languages? Is C# faster than JavaScript at all?
I mean, apart from JavaScript, potentially going into dynamic dynamic typing.
Oh, typing.
No, there isn't. I mean, it's basically, it all runs on the .NET runtime. It's all JIT compiled, so it's all pretty fast. Yeah.
Just to clarify a little bit on the last thing about mouse overs or raycasts.
Yeah.
So if I have 30 objects in a room that have a mouse over script on them, is that every time that the mouse moves, is that?
You mean like a function on mouse over?
Yeah.
I mean, basically, the way Unity does it internally is we do one raycast each frame to at the mouse position to figure out what is below, and then we call the appropriate functions. So it's not like you're gonna die doing that. I mean, it's usually not. I mean, it doesn't show up in any profiler.
So it would be better to either do a calling mask or disable the scripts when they're at the range.
That doesn't affect the raycast actually. I mean, right now it doesn't. I mean, don't worry about that. I mean, in the talk I said don't do raycasting, but the truth is don't do raycasting too much. I mean, doing like 10 raycasts a frame, well, perfect. No one is going to complain about that. But if you just have like 500 people walking around and they all do a raycast and they all do it against mesh colliders, that's going to get slow. All right. Well, thank you.